You've been told your thoughts create reality. You've been told quantum physics proves it. You've been told that observation collapses the wave. That consciousness sculpts the universe. That manifestation isn't belief, it's science. Let me tell you something, you've been lied to. Not completely, but just enough that the real truth, the kind hiding in plain sight, has been buried beneath layers of pseudoscience, wishful thinking, and motivational sound bites that sound profound, but collapse the moment you apply pressure. They sparkle, they inspire, and then they evaporate. Here, that's what nobody tells you. Even the scientists who discovered quantum mechanics, the sharpest minds to ever probe the foundations of reality, don't actually agree on what is happening at all. They can predict outcomes with almost frightening accuracy. They can build machines, technologies, entire civilizations on the math. The equations work flawlessly. But ask them what's really going on underneath those equations, what reality itself is doing, and you'll get 8 completely different answers from 8 equally brilliant physicists. And in this video, I'm going to show you why that isn't a flaw. It's the point. Ready? Let's go deeper. Before we step into the battlefield of interpretations, I need you to understand something fundamental, something that will give you permission, real permission. Permission to stop blaming yourself for feeling confused. That confusion isn't yours alone. It belongs to everyone. It belongs to Nobel Prize winners, to textbook authors, to researchers who spend entire lifetimes trying to understand what actually happens when a particle is measured. Because here's the truth most people never hear. Quantum mechanics works perfectly. Its predictions match experiments to absurd, almost uncomfortable levels of precision. But what it means, what is truly happening in reality, remains an open question. And not open like we'll crack it next year. Open like we've been arguing about it for over a century and we're nowhere near agreement. Wolfgang Pauli, one of the central architects of quantum theory, said it bluntly. To fully answer what's happening, we would need a complete theory of consciousness itself. David Mermin, the physicist behind the Ithaca interpretation, went even further. He stated plainly that consciousness lies outside the scope of what quantum mechanics can solve. Let that land. The people who understand this better than anyone alive are openly admitting, we don't know. And here's where things become genuinely interesting. That not knowing isn't a failure of intelligence. It's not because the right genius hasn't arrived yet. It's because the question itself intersects with something we barely know how to touch at all. Consciousness, observation, the act of looking. So if you felt lost trying to understand manifestation, if you've struggled to reconcile spiritual intuition with scientific rigor, if you've wondered whether your thoughts actually do anything, welcome to the club. You're in very good company. The confusion you feel isn't weakness, it's wisdom. It means you're paying attention. Now let me show you why this mystery actually matters. The problem begins innocently enough with what physicists call the measurement problem. And trust me, once you truly see it, you can't unsee it. Here's the setup. In the quantum world, particles don't exist in definite states until they're measured. Before measurement, an electron isn't here or there. It exists in something called a superposition, a ghost-like blend of all possible positions at once. The math describes this as a wave function, not a wave of water, not a wave of sound. A wave of probability, a wave of potential reality. Then you measure it, and the moment you do, boom, the wave collapses. The electron snaps into a single, definite position. All other possibilities vanish. One outcome becomes real, but here's the kicker. Nobody knows why. Nobody knows what causes the collapse. Nobody knows what actually counts as a measurement. Nobody knows where the boundary is between the quantum world of superposition and the classical world of solid outcomes. This isn't fringe speculation. This is the central, unresolved problem of quantum mechanics, the thing that keeps physicists awake at night. Erwin Schrödinger, one of the founders of the theory, hated this implication so much that he invented a thought experiment to expose how absurd it sounded. You've heard of it, Schrödinger's cat. A cat sealed in a box, its life tied to a quantum event. According to the math, until you open the box and observe, the cat is both alive and dead at the same time. Schrödinger wasn't saying, look how cool quantum mechanics is. He was saying, this is insane. The math is dragging us into nonsense. And yet, the math works. The experiments confirm it. Particles really do behave as if they exist in superposition until observed. The absurdity isn't imaginary. So what's going on? That's where interpretations enter the picture. Because the math doesn't tell you what's happening. It only tells you what you'll measure. Interpretations are attempts, competing, conflicting attempts, to answer the question beneath the question. What is reality? What role does observation play? Does the universe exist independently of us, or are we somehow involved in its unfolding? And here's what I want you to hear clearly. Every interpretation runs straight into consciousness. Every single one. Not because physicists are secretly mystical, but because the confrontation emerges directly from the experiments themselves. You cannot avoid it. It's not a glitch in the theory. It's a feature of reality. So let's walk through the major interpretations. Let's hear what the experts actually say. And let's understand why, after more than 100 years, there is still no winner. Shall we step onto the battlefield? The first interpretation, the one most physicists were taught, the one that dominated classrooms for decades, is called the Copenhagen interpretation. Named after the city where Niels Bohr worked, it's elegant in one specific way. It refuses to answer the question. Copenhagen says this: don't ask what's happening before measurement. The question is meaningless. Quantum mechanics describes what we observe, not what exists independently. Before measurement, there is no reality to speak of. The wave function is simply a mathematical tool for calculating probabilities. And when you measure, the wave function collapses. How? Why? What qualifies as a measurement? Copenhagen doesn't say. It shrugs politely and tells you to shut up and calculate. And for a long time, that was enough. The math worked too well. It delivered predictions, technology power. Asking deeper questions almost felt ungrateful. You want results. Here, you want machines. Here, you want philosophical clarity. Sorry, not included. But there's one thing Copenhagen can't escape. Measurement requires an observer. Something has to look. Something has to register. Something has to mark the moment where possibility becomes fact. And that's where the silence begins to speak. Interact, and that something, whether it's a machine, a photon detector, or a human eye, is itself made of quantum particles too. So the question becomes unavoidable. Where does the chain end? When does the wave function actually collapse? John Wheeler, one of the sharpest and most imaginative physicists of the 20th century, pushed this question all the way to its edge. He proposed what he called the participatory universe. The idea that observers aren't merely passive witnesses watching reality unfold. We are participants. Our observations play an active role in bringing the universe into being, not in a mystical, New Age sense. In a literal, physical sense, encoded directly into the structure of the experiments themselves. And yet, Wheeler also warned against taking this too far. He famously said, "Consciousness has nothing to do with the quantum process." Observation, yes. Consciousness, maybe not. That contradiction should make you uncomfortable. Because how do you separate the two? What exactly is observation if not an act tied to awareness in some form? Copenhagen doesn't answer that. It gives you a framework that works astonishingly well in practice, but it leaves the deepest question suspended in midair. What is observation? And if everything is ultimately quantum, where does observation begin at all? Most people hate this uncertainty. They want solid answers. They want to know what's real. They want clarity. But Copenhagen responds with a blunt simplicity. Reality is what you measure. Nothing more, nothing less. And inside laboratories, inside experiments, inside the pragmatic world of applied physics, that's enough. For all practical purposes, a phrase physicists love, Copenhagen works. FAP. For all practical purposes, but philosophers don't live there. Mystics don't live there. And people like you don't live there either. You don't just want a tool, you want the truth. And that hunger, that refusal to settle for good enough, is what drives the other interpretations. So let's turn to the interpretation that takes the opposite stance. The one that says the wave function never collapses. Not once, not ever. The one that claims every possibility becomes real. In 1957, a graduate student named Hugh Everett proposed something so radical, so shockingly bold, that it took decades for the physics community to even begin taking it seriously. He said the wave function doesn't collapse at all. It never collapses. Every possible outcome of every quantum measurement actually happens, not metaphorically, literally. The universe splits. Reality branches, and every version of you, every possible you, experiences a different outcome in a different branch of reality. This is the many worlds interpretation. And before you dismiss it as science fiction, understand this. This is real science, peer-reviewed, debated at the highest levels. Favored by many cosmologists and quantum theorists precisely because it takes the mathematics at face value. Maybe too seriously, but seriously nonetheless. Here's how it works. When you measure a particle's position, the wave function doesn't collapse into a single outcome. Instead, the universe branches. In one branch, the particle is here. In another, it's there. Both outcomes are real. Both universes exist. You just can't see the others because you're stuck in one of them. No collapse, no mystery mechanism, no privileged role for observation. Just the math unfolding exactly as written, every possibility realized, every quantum coin flip spawning new worlds. It sounds insane, and yet here's what makes it compelling. Many worlds is deterministic. There's no fundamental randomness, no spooky collapse process injected by hand, just the wave function evolving smoothly according to Schrödinger's equation. Everything that can happen does happen. We simply experience one thread in an infinite tapestry. And if that's true, then there are versions of you making every possible choice. A version of you that said yes when you said no. A version that turned left when you turned right. A version living the life you once dreamed about, and another suffering the consequences you narrowly avoided. Sit with that. Does it feel like comfort or existential dread? For some people, many worlds is liberation. It means every path is honored, every possibility fulfilled. Nothing is wasted. For others, it's horror. It means there is no single you, no privileged identity, just infinite fragmentation, countless copies of self scattered across parallel realities. And here's the catch, a big one. If every outcome happens, if every branch is equally real, then no branch is special. The version of you reading this right now is no more fundamentally real than the version in another branch that clicked away moments ago. Probability stops being a basic feature of reality. It becomes a bookkeeping tool, a way of counting branches. And consciousness in the many worlds view doesn't collapse anything. It doesn't choose. It doesn't influence outcomes. It simply rides along, experiencing one branch while remaining blind to all the others. So does that solve the measurement problem? Or does it just trade one mystery for another? Now let's look at a third approach, one that tries to carve a middle path. One that says maybe the collapse isn't mysterious at all. Maybe it's just physics we haven't fully accounted for yet. This is decoherence. And it's the closest thing quantum mechanics currently has to a partial consensus, not because it answers every question, but because it explains something crucial that the other interpretations struggle with. It explains why we don't see quantum weirdness in everyday life. Here's the puzzle decoherence addresses. If particles can exist in superposition, occupying multiple states at once, why don't large objects do the same? Why isn't your coffee cup both on the table and not on the table simultaneously? Why does quantum strangeness vanish the moment things get big? The answer is the environment. Nothing in the universe exists in isolation. Every object is constantly interacting with its surroundings. Photons bounce off it. Air molecules collide with it. Heat radiates from it. These interactions entangle the object with its environment in unimaginably complex ways. And that entanglement destroys the delicate quantum coherence required for superposition. It's not that the wave function collapses. It's that the superposition becomes so thoroughly scrambled, so hopelessly entangled with trillions of environmental particles, that it becomes effectively invisible. For all practical purposes, there it is again. The object behaves classically, definitively. No observable superposition, no quantum ambiguity. This is decoherence. The process by which quantum possibilities are washed out by environmental noise. And it happens fast, absurdly fast. For a particle the size of a grain of dust, decoherence occurs in less than a billionth of a second. For anything larger, the quantum world disappears almost instantly. So, problem solved, right? No mysterious collapse, no consciousness loophole, just physics doing what physics does, except not quite. Because decoherence doesn't actually solve the measurement problem, it just pushes it back. Yes, the environment destroys superposition. but it doesn't explain why one outcome is experienced rather than another. It explains why interference disappears, not why reality selects a single result. And right there at the edge of that explanation, the mystery quietly waits. Position, but here's the problem. The environment is made of quantum particles too. So when does its wave function collapse, or does it collapse at all? If everything is entangled with everything else, the object, the environment, the measuring device, the observer, where exactly does the chain stop? Decoherence tells you why you don't see superposition in daily life. It explains why the quantum strangeness fades the moment systems become large and messy. But it doesn't tell you what reality is. It doesn't tell you whether the cat is actually alive or dead before you open the box. It only tells you why the superposition becomes unobservable. FAP, for all practical purposes, that phrase again. Decoherence is incredibly powerful. It's essential for building quantum computers. It explains how classical physics emerges from quantum laws. But does it answer the deep question? No, it doesn't. And that brings us to the heart of the matter, the thing every interpretation collides with, the thing none of them can escape. The observer, consciousness itself. And this is where things stop being merely strange and start becoming profound. Here, as something most people don't realize, the role of consciousness in quantum mechanics is not a new age add-on. It's not pseudoscience. It's not manifestation coaches hijacking physics to sell courses. It's real, it's unavoidable, and it's baked into the foundations of the theory itself. But you have to listen to what the experts actually say, not what motivational speakers claim they say. Listen carefully. Wojciech, one of the leading researchers in quantum decoherence, stated it plainly. To give a full answer to the measurement problem, we need a model of consciousness. Not maybe, not eventually. Now, consciousness is part of the equation. David Bohm and Basil Hiley, who spent decades developing an alternative formulation of quantum theory, wrote this. The intuition that consciousness and quantum theory are in some sense related seems to be a good one. These aren't mystics. They're physicists. David Mermin, the architect of the Ithaca interpretation, went even further. He said consciousness lies outside the scope of what quantum mechanics can currently address. Not because it's irrelevant, but because the theory simply isn't equipped to touch it yet. And John Wheeler, brilliant, careful, relentlessly rigorous John Wheeler, proposed the participatory universe while simultaneously warning against mysticism. He said observation matters. Participation matters. We are not passive spectators recording a pre-written script. The universe does not fully exist until it is observed. But here's the paradox Wheeler couldn't escape. How do you have observation without consciousness? How do you separate the act of measuring from the experience of knowing? You can't, not cleanly, not honestly. Every interpretation runs into this wall. Copenhagen needs an observer to collapse the wave. Many worlds needs consciousness to explain why you experience one branch instead of all of them. Decoherence needs something to define when environmental interaction becomes measurement. Even pilot wave theory, the Bohmian interpretation, struggles to explain how consciousness fits into its otherwise deterministic framework. This encounter with consciousness arises directly from the theory itself and from experimental demonstration. That's not a quote from a self-help book. That's language taken straight from peer-reviewed physics literature. You cannot avoid it. So here's what that means for you, for your intuition that something is connected, for your sense that consciousness matters, for your quiet suspicion that the purely materialist story, reality exists independently, we're just biological machines observing it, is incomplete. You're not crazy, you're seeing something real, something the experts themselves openly acknowledge. Universal connectedness isn't mysticism, it's Bell's theorem. Observer participation isn't manifestation hype, it's Wheeler's physics. That feeling that consciousness and reality are intertwined. That intuition is shared by some of the greatest scientific minds who ever lived. But, and this is critical, that does not mean your thoughts create reality like a cosmic vending machine. It doesn't mean you think hard enough and the universe spits out a reward. It means the relationship is deeper, more subtle, more profound, far beyond any sound bite. So what are the implications? What does this actually mean for how we live? Let's go there. In 1964, A physicist named John Stuart Bell proved something that shattered our classical intuitions about reality. He proved that if quantum mechanics is correct, and every experiment says it is, then the universe is fundamentally non-local, interconnected, not in a vague spiritual sense. In a precise mathematical, experimentally verified sense. This is Bell's theorem, one of the most profound results in the history of science. Here, is what it means. If two particles interact and then separate, no matter how far apart they move, light years apart even, they remain connected. Measure one, and the other responds instantly. Not because a signal travels between them, but because they were never truly separate. They're parts of a single quantum system. Einstein hated this. He called it spooky action at a distance. He believed it meant quantum mechanics was incomplete, that there must be hidden variables restoring locality. Bell proved him wrong, not with philosophy. With mathematics, there are no hidden variables that can rescue locality. The universe really is non-local. And experiments have confirmed this again and again, with photons, with electrons, with increasingly sophisticated setups designed to close every possible loophole. The conclusion is unavoidable. Universal connectedness is real, but here's what that does not mean, and I need you to hear this clearly. It doesn't mean your thoughts instantly affect distant objects. It doesn't mean you can manifest a parking space by visualizing it. Bell's theorem describes correlations between entangled particles, not magic, not mind over matter. That distinction matters because the manifestation industry loves to point at quantum entanglement as proof, and they're misusing it. Entanglement shows that reality is stranger than classical physics ever imagined. It shows that separability, the idea that objects are fundamentally independent, is false. But it does not give you telekinesis. What it does give you is this: a universe where everything that has ever interacted remains connected at a level deeper than space and time. A universe where separation is an illusion, useful, functional, but not fundamental, where the boundaries between self and other here and there are provisional. Does that make you feel smaller or larger? Because for me, it's both. Smaller because I'm not separate, not special, not the center of the story. Larger because I'm connected to everything, woven into the fabric itself, a single thread in an infinite tapestry. And just when you think that's as strange as it gets, some interpretations, like the transactional interpretation, suggest that causality itself might run both ways in time. And that's where things start bending in ways we're barely prepared to understand. That when you observe a photon arriving from a star 100 light years away, your eye may be sending a wave backward in time, all the way to the moment that photon was emitted, not metaphorically. Mathematically, the future influencing the past, the observer completing the loop. Is this true? We don't know. It's an interpretation, but the equations allow it. And that alone should tell you something. Reality is far stranger than you were ever taught to believe. So let's come back to the question you're probably asking now, the question beneath all of this. What does this mean for me? For my life? For how I think about consciousness and reality? John Wheeler called it the participatory universe. The idea that we're not merely observing reality from the outside, we're participating in it. Our measurements, our observations, our interactions don't just reveal what's already there, they help determine what becomes there. But here's the uncomfortable truth. Participatory does not mean controllable. It does not mean you get to decide outcomes. It doesn't mean the universe bends to your wishes. It means you're involved in a process vastly larger, deeper, and more complex than your individual will. Think of it like a dance. You're on the floor, your movements matter, they influence the dance. But you're not dancing alone. You're dancing with partners you can't see, to music you didn't compose, in a hall you didn't build. Participation, yes. Control, no. And this is exactly where most manifestation teachings go wrong. They take the participatory universe and turn it into a promise. They tell you that because observation matters, your thoughts shape reality, that consciousness is primary, that you are the creator. But that's not what the physics says. What the physics says is quieter, more subtle, more humbling. It says consciousness and reality are entangled in ways we do not yet understand. It says observation plays a role we cannot ignore. But it does not say you are the author. That difference matters. One version turns you into a god, the other makes you a participant. One inflates the ego. The other integrates it into something far larger. And here's what I want you to sit with. Maybe the mystery itself is the answer. Maybe the fact that we don't know, that even the experts can't agree, is telling us something essential. That reality is too vast, too strange, too multi-layered for any single story to contain. Wheeler understood this before he died. He said our current understanding of quantum mechanics may be like believing the Earth is flat before discovering it's round. We're missing something fundamental, something that will rearrange everything once it finally comes into view. So what does that mean for how you approach all of this? For how you think about consciousness, quantum mechanics, and the relationship between them? It means you hold it lightly. You stay curious. You resist the urge to collapse the mystery into a slogan. You value the questions more than the answers, because the questions are what keep you awake, alive, engaged. David Bohm said something quietly beautiful near the end of his life. He said that trying to understand quantum mechanics taught him one thing above all else: that reality is always more than we can grasp, that every answer opens into deeper questions, that the universe is not a puzzle to solve, but a mystery to live inside. And maybe that's the real implication. Not what we can control, but how we relate to what we cannot. Before we close, I want to tell you something. This is episode 26 of the Observer Effect series. 26 journeys into the deepest questions reality has to offer. And we've just spent 30 minutes approaching the mystery from the physics side, from particles and waves, from measurement and math, from interpretations that still cannot agree on what's happening beneath the equations. But there's another side to this, the consciousness side, and in episode 27 we're going to begin there and move toward the encounter from the opposite direction. Here, that's what I'm going to show you. In the 1980s, a neuroscientist named Benjamin Libet ran an experiment that shook the foundations of what we think we know about free will. He asked people to move their wrist whenever they wanted, a simple, spontaneous choice. But he measured their brain activity while they did it. What he found was unsettling. The brain showed a readiness potential, an electrical signal indicating a decision, before the person reported consciously choosing to move. The brain decided first. Consciousness arrived later. And that raises a question so deep, so uncomfortable, that even physicists can no longer ignore it. Do you have free will, or does your brain make decisions that your consciousness merely experiences after the fact? In 2008, another researcher, John Dylan Haynes, pushed this even further. Using brain imaging, he could predict which button a person would press up to 10 seconds before they consciously decided. 10 seconds. That's not a delay, that's a chasm. When Haynes was asked what this meant, he said something stunning. It doesn't rule out free will, but it makes it highly implausible. Now here's where this connects to everything we've explored today. John Bell, the same Bell who proved universal connectedness, said something most people overlook. He said quantum mechanics cannot become a complete local theory unless we allow experimenters to have freedom. Free will is no longer just philosophy. It's appearing in the equations, in peer-reviewed journals, at the foundations of quantum mechanics itself. And centuries earlier, an 18th century philosopher named George Berkeley said something that sounded absurd until you place it beside modern physics. He said, "To be is to be perceived. Nothing exists unless it is observed." When people mocked him, he had a reply, one that intersects directly with consciousness, observation, and the participatory universe Wheeler described. Episode 27 is going to take you there, into experiments that challenge your sense of agency, into philosophy that anticipated quantum strangeness centuries ahead of time, into the hard problem of consciousness, a problem physicist David Chalmers says may be just as unsolvable as the measurement problem itself. So far, we've been moving from physics toward consciousness. Next time, we move from consciousness toward physics. And when those two paths finally meet, when you hold both mysteries at once, something shifts. Not because you finally understand, but because the question itself changes. The playlist and the next episode are linked in the description below. If this journey is calling you, if you're ready to go deeper into the encounter, I'll see you in episode 27. Until then, stay curious, stay rigorous, and stay awake to the mystery. This is Observer Effect, and the real observation is only just beginning.